So the first thing they're going to do are volcanoes. Now remember, we have these beautiful Icelandic volcanoes that we can absolute date. And this is the data. This is the data that Team 1 has, Team 2, Team 3, and Team 4. Now for Team 1, 3, and 4, they are all given a specific place to look to get them started on labeling the Icelandic volcanoes and then the mid-latitude volcanoes. They're going to start with the Icelandic volcanoes because they have that unique signature. Conductivity up, nitrate down. And here is Team 1 is told to look at Hekla, which took place in 1970, located between samples 600 and 700, locate that anomaly and label it. 1970 Hekla. So the ones in black are Icelandic volcanoes. So they can label those volcanoes. The more items they label, the better off they are, because the more dates that they will have that they will be fairly confident of. So they should do the Icelandic ones and then go through and do the mid-latitude ones. They should actually label every single volcano they have. You see we have a problem because this is real science and this ice core did not evenly distribute the events on all 4 strips so that everybody would have an equal amount of work to do, which is something else that you have to take into account when you do this in the classroom. Team 2, no Icelandic volcanoes erupted during the time frame represented on this section of the strip. So they are asked to go to samples 3100 to 3200 and label the Carrington super flare, which took place at that particular point in time. It will be quite obvious because it was quite massive, probably the largest geomagnetic storm ever recorded. At that point in time, we had telegraph for communication, and the energy from that traveled along the telegraph lines and actually set paper on fire in telegraph offices. So it was a very massive event. But they can date all of the mid-latitude volcanoes that are on their particular strip as well as that. So these are historic volcanoes. We know exactly what date they happened. You have the additional unique Icelandic signal to help date those particular nitrate anomalies. So the second part of this investigation is to label the solar proton events. Now the sun has a cycle, 11 years from increasing sunspot activity to the polar reversal, and then we go the other way again, more and less. It's actually a 22-year cycle overall, and when it is more active, of course, there's more sunspots, there's more coronal mass ejections during those protons, actual photons, not radiation, that hits the Earth's atmosphere also, but also protons manage to slide along the Van Allen radiation belts, slip into Earth's atmosphere in the polar regions, enter the upper atmosphere, chemistry happens, ionizes the atmosphere, products are formed, one of them being nitrates, and then you have nitrate deposition on the surface in the polar regions. And you see these solar proton events. Every one of those little white specks is a proton that is on its way towards Earth, and they will end up producing ionization and nitrate deposition in the polar regions. Nitrates are different than other ions in the atmosphere. They simply fall due to gravitational deposition right to the surface. So Team 1 will have a lot. That was when the sun was very active and producing a lot of solar proton events. Team 2, we have the end of the Dalton minima in 1833, so there aren't as many there. And Team 3, this is the start of the Dalton minima and the end of the monominima, so again, but there are a lot of them right in there in between. Team 4, here we go again, rats. That is, that entire length of time is when the Maunder minima starts in 1645, and so there are no solar proton events on that particular ice core strip. So what you will do with Team 4, you know, if you have 4 students all with one different strip and they're all working together, then everybody can work together. But if everybody's individually doing their own strip, you might have these people researching maybe some of those volcanic eruptions, researching anything that's part of that background that you might want to print out and have them look into some historical aspect of it. There's a lot of different things you can do. Team 4 makes up for that because when it gets to the final end point, the solar, the supernova, those are going to be on the 4th strip. So they can go down through, they can use the absorption units they've already dated volcanoes, so there are dates on their strip already. They can look at the amount of nitrate absorption, the counts. They can use that and what they've already labeled and dated. They can kind of count little cycles. You can kind of see the cycles going up and down. You can use that as an estimate for how many years in between. And at this point in time, you actually can lay a ruler down and measure from 2 dates that you're fairly sure about or have a lot of confidence in and determine how many years per centimeter and use that also. So there's all these different ways of going about finding an anomaly or a date for an event and deciding which one of those spikes is associated with that particular event. Just like, and your students will start to ask you, because teachers start asking me when I'm doing this with them in a workshop, but how do I know? How do I know? Well, this is real science. You do the best you can and then determine how confident you are in your results. But remember, this is just one set of data points. As Gisela will tell you and tells everybody, I am not saying that the date I have found for Cas A is the date for Cas A. We need more data points. We need more research. We need more. So it gives them a better idea of how things work. So we come to the final part, which fortunately includes Cas A, Tycho, and Kepler, 3 supernova remnants that the Chandra X-Ray Observatory has imaged, which makes this entire investigation legitimate and allowed me to use Gisela's ice core data for the Chandra Observatory. And so nitrate anomalies and supernova events. So here we have another example, like Alfred Wegener, who thought outside of his discipline to think that maybe continents actually moved around the surface of the Earth. As I said, Gisela was her project, the GISP-2 H-core project that she was the PI on, one of the 2 PIs on. She was interested in solar proton events because they wanted to see if they could go back in time and determine the solar activity beyond what we had started recording in the early 1600s. So when they were all done and analyzed all their data, labeled all of the nitrate anomalies that they could, there were anomalies left behind. And so she said, I wonder if high energy radiation coming in from supernova events can cause nitrate deposition in the polar regions. And she was attacked. She is still being attacked because there are scientists that say you cannot possibly correlate an anomaly, a nitrate anomaly, with a supernova event. There are other publications from there's one group of Japanese who have published a research paper. They say they have correlated a nitrate anomaly in the record with the Vela supernova remnants. So there are scientists that say yes and scientists that say no. Controversial science. That's real science. My friend Jean-Pierre Normand is a famous science fiction and fantasy illustrator, and he very kindly provided several illustrations to go along with the ice core materials.